Hello again. In this video, I'm going to go over this homework problem from 4.7. And so in this problem, we're supposed to evaluate the following limit using L'Hopital's rule. Okay, so let me show you how to work this out. So we're going to use a little bit of a trick here to find this limit. Before we actually find this limit, we're going to rewrite this function inside of it right here, using this property over here. So this property basically says that if you take e and raise it to the natural log of f of x, it's equal to f of x. And that's because e and ln are inverse functions of each other. And so they sort of cancel out here, and you're left with this function that's inside the logarithm. Now, if you want to convince yourself that this works, on your calculator, take e and raise it to the ln of like 2, and you'll see that it's equal to 2. Okay? So we're going to take advantage of that property. Okay, so we're going to take this function here, and we're going to rewrite it. And so we're going to rewrite it as e raised to the ln of that function. Okay, those are equal, right? Again, these cancel out. The e and the ln cancel out, and you're just left with this function here. Okay, and now we really want the limit of this function as x goes to infinity, right? So let's find this limit. The limit of this as x goes to infinity would be equal to the limit of this right-hand side as x goes to infinity. Okay, and then to find this limit, we're going to take advantage of another property, a property of limits that says the limit of e to the f of x as x goes to infinity, that's the same as e raised to the limit of f of x as x goes to infinity. So in other words, you can find the limit of this function first as x goes to infinity and figure out what that number is. And then this limit on the left-hand side is simply e raised to that number. Okay, so that's what we're going to do over here. Okay, so to evaluate this limit, we're actually going to find the limit of the natural logarithm as x goes to infinity first. And then once we figure out what this number is, this limit right here is just e raised to that number. Okay, and so we're going to just focus in on finding this limit. I'm going to do that on the side, and then after we find what that limit is, then we'll just come back and plug that number into here, and we'll be able to tell what this limit is. It'll just be e raised to that number. Okay, so let's find this limit. Oh, there should be a natural log in front here. Okay, I left that off. Okay, so let's try to figure out that limit. Okay, again, there should be a natural log in front of that. I just left it off. Okay, so let's talk about finding this limit. First of all, I think it's a valid question to ask why we even took this function here and rewrote it this way using this property. Why did we do that? Okay, that's a valid question. And I think the answer is we're trying to take advantage of the properties of logarithms. Notice right here, we can actually simplify this logarithm before we actually take the limit as x goes to infinity. We're allowed to take this exponent up here and multiply it in front of the natural logarithm. That's a property of logarithms. Now, we wouldn't have been able to do that if we hadn't rewritten it like this first. And so that's really the reason we're doing that, is we used this property solely because we wanted to take advantage of the properties of logarithms, namely the one that allows us to take the exponent up here and multiply it in front of the logarithm. Okay, so let's do that. Okay, so this is the same as x to the fourth times the natural log of 1 plus 7 over x to the fourth. Okay, and let's see if we can't evaluate this limit. So look, x is heading towards infinity, right? So this x to the fourth is just going to go towards infinity as well. Okay, notice here, 7 over x to the fourth, that's going to get closer to 0 because x is getting bigger and bigger, which means this is getting closer to 1, this entire thing here. And then you're taking the natural log of that number, right? So this is getting closer to 1. But then you're taking the natural log of that number, and the natural log of 1 happens to be 0. So really, this entire natural logarithm is getting closer to 0. And so overall, what's happening is, as x is getting larger, this right here is getting larger as well. So it's a really big number that's just getting bigger and bigger. And you're multiplying it by a number that's getting closer and closer to 0. Now remember, this will never reach 0, just like this never reaches infinity. And of course it doesn't, because infinity is not a number. But this never reaches 0. Okay, it just gets closer to 0. And so you need to think of this as a really, really large number that keeps getting larger and larger, being multiplied by a number like 0.00001, right? A number that's just getting smaller and smaller. Now, unless we know the details of what these numbers actually are, we can't compute what this is going to get closer to overall. Okay, and so that's called an indeterminate form. We cannot determine the limit in the form that it is in right now, unless you use a table. Now, if you wanted to use a table and a calculator, then you might be able to determine it by looking at the table of values, but that requires a lot of calculation. Okay, so here's what we're going to do. All right, since it's indeterminate, what we're really trying to do here is we're going to try to change this multiplication into division. Division doesn't really make it easy for us to find this limit. It makes it difficult. But if we had multiplication is more difficult. If we had division, it would be a lot easier. Okay, so we're going to try to create division here. And here's how we're going to do it. We're going to take this natural logarithm, and we're actually going to divide it by 1 over x to the fourth. Now, notice these are equal, right? Because when you divide by this fraction, you can flip, it's the same as flipping it and multiplying by it. So if you were to flip this, it would be x to the fourth over 1 times the logarithm. So these are equal, okay? All right, and now let's try to determine the limit. Okay, again, this top piece is heading towards 0. And then notice this bottom piece is also heading towards 0 because it's 1 over a really large number. And so now the form that we have is 0 divided by 0, which is good news, because if you remember, L'Hopital's rule is only valid when we have two different forms, either 0 over 0 or infinity over infinity, plus or minus infinity over infinity. Okay, so you can't use L'Hopital's rule unless you have one of those two forms. Okay, so we couldn't have used L'Hopital's rule here. Okay, and that's the reason we created division, because multiplication doesn't lead to a valid case for L'Hopital's rule. Okay, but now that we've rewritten it like this with division, we do have a form where we can use L'Hopital's rule, right? 0 over 0. Okay, so now we're going to use L'Hopital's rule to evaluate this limit. And if you remember, L'Hopital's rule tells us that the limit of f of x divided by g of x is the same as long as we have one of these two forms for the limit. That's the same as the limit of f prime of x divided by g prime of x as x goes to infinity. Okay, so basically we need to find the derivative of the top one and divide it by the derivative of the bottom one, and then evaluate the limit as x goes to infinity, and that'll be the same as this limit. Okay? So what I'm going to do here is I'm going to find the derivative of the top piece on the side, and then once I'm done, I'll just fill it in up here. Okay, so let's find the derivative of this top piece. Well, if you're going to find the derivative of this, you're going to have to use the chain rule, because this is really a composition of two functions, right? The inner function is 1 plus 7 over x to the fourth, and then the outer function is like ln of x. Okay? So let's write it that way. So let's say, I'm just going to write it out so we can see this. The outer function is ln of x, and of course your inner function would be 1 plus 7 over x to the fourth. Okay? And then if you remember, the chain rule tells us that the derivative of a composition of functions f composed with g, that's the same as f prime evaluated at g times g prime. And of course, this is called the outer derivative, and this one's called the inner derivative. Okay, so let's see if we can't find this derivative using the chain rule. So f prime. Okay, so the derivative of natural log of x. Okay, well, that's just 1 over x. Okay, and then you have to evaluate that derivative at g of x. So f prime evaluated at g. In other words, f prime evaluated at, here's g, right? So 1, f prime evaluated at 1 plus 7 over x to the fourth. Okay? And of course there, you're plugging this into this function here, right? What does this function do to anything that you plug into it? It just says 1 over whatever you plug into it, right? That's what it does. So when I plug this into this function, I'm just going to get 1 over that. Okay? That's what this function does, right? Anything you plug into it, it just says 1 over whatever you plugged into it. So it's just going to take, this is what I'm plugging into it, so it's just going to say 1 over that. Okay, so there's my outer derivative, right? That's f prime time evaluated at g. And now we need g prime. Okay, and so to find this derivative, I think it'd be easier to just rewrite it first. Let's write it as 1 plus 7 times x to the negative 4. Remember, those are the same thing. 7 over x to the 4 is the same as 7 times x to the negative 4. And then that way, finding the derivative is a lot easier. Of course, the derivative of the 1 is 0. And then the derivative of the second piece is just negative 4x to the negative 5 times the 7. Using the power rule, right? You multiply by the negative 4 in front, you multiply that negative 4 by the 7, and then you subtract 1 from the exponent, and you get x to the negative 5. Okay, so that's your inner derivative. And then when you multiply these two together, the outer derivative and the inner derivative, that gives you the derivative of this function here. Okay, so there's your outer derivative, and then that's your inner derivative. And I'm just going to write that as negative 28. Okay, so that's the top part. That's the derivative of this function here. Okay, and then we need the derivative of this bottom piece. Okay, but that's pretty straightforward. You just want, before you find that derivative, just rewrite this as x to the negative 4 first. Same old trick that we've used down here. And so the derivative would be negative 4x to the negative 5. Okay, so that's the derivative of the bottom function here. Now notice the x to the negative 5 cancels out. That's really nice, right? And then here, negative 28 over negative 4 is just 7. Okay, and so it looks like you just get this whole thing right here is 7 times this piece here. Now don't be confused about where the 7 is. This is 7 over 1. So the 7 is on top, not on the bottom. Okay. And now let's try to evaluate this limit. Okay. So as x goes to infinity, this is heading towards 0, which means the bottom is getting closer to 1. And so it looks like you end up getting closer to 1 times 7, right, which is just 7. Okay. So now, going back, we just determined this limit right here. We figured out what this limit was. The limit as x goes to infinity of the natural logarithm. That's equal to 7. But the limit we were trying to find originally was this limit, right, which is equal to this limit, which is equal to this limit. And we know what this limit's equal to up here, right? This limit right here is 7. And so this is going to be e to the 7th power, because this is getting closer to 7. And so that's this limit, the original limit that we were trying to find. Okay. Going back up to here, right? This limit right here, that's the one we were trying to find. So this is getting closer to e to the 7th. Okay, so I hope you found this video helpful. In the future, I'll continue to work some problems from the homework, and hopefully you'll get a chance to look at some of those videos as well. Thank you for watching. Bye-bye.